Now I will very shortly give the reins over to my colleague Pasi and have him share his computer, his presentation, and his thoughts with you guys. But before we start, I just wanted to welcome all of the new people who have signed in over the last hour. I hope many of you heard the last presentation, and I hope you're excited to hear about WebGL. Before we start, I just want to make everybody sure that they know that we are recording this session, and we will be sending out very shortly the recording of the session so that you can access this online at any time convenient for you. Feel free to share that recording with your friends and your family or colleagues or whoever might be interested to learn more about Qt. If you have questions during the session, I see that a lot of you are already using the Q&A panel in the WebEx tool. Feel free to do that. I and my colleague Anka, we are both monitoring that and trying to reply to as many of your questions as possible. However, we might not be able to catch them all, as there's a lot of people online here, which is great. We will get back to you if we can't answer your question during the session. I'll try to collect as many questions as possible for the end of the session or during the session if anything fits in there. So yeah, we'll try to get back to you with as many answers as possible, and if not now, then a little bit later. And with that, I think it's time for me to hand over to Pasi Keränen. So I'll give you the presenter rights now, Pasi, if you're ready. And then you have to unmute. Now I've unmuted you.
Okay, hello.
Hello, Pasi. I can hear you well.
Great. So let's get started. The topic of this talk is the enabling direct WebGL in Qt Quick 2. But let me first introduce myself because I'm rather new in the Qt community, so probably not many people know me yet. So I've been programming graphics since 1983 with the 8-bit computers, 2D stuff, of course, in the beginning. I learned OpenGL 1 in the 1990s, did some more serious UI development after that, but then I joined Nokia's Graphics Knowledge Center in 2005, which was basically all about doing 3D graphics on the mobile side. I was the technical lead from Nokia side to make the Symbian graphics architecture more hardware accelerator friendly, because at the time it wasn't really. I have participated in Khronos standardization. I have participated in open code. My name can be seen in the EGL 1.4 specification, and I was the chairman of the OpenWF 1.0 working group in Khronos. I joined WebGL last year, and I'm part of the team that has done the Qt data visualization that many of you probably have seen if you have gone to any of the trade shows or seen our marketing material, because it is usually pretty visible there. And I have implemented the QiCanvas 3D that I'm now going to be talking about. And in general, around the office, I'm known as the graphics dude. So let's look at the overview. So first I'm going to be talk a bit about like what is WebGL, a short history of WebGL, and show you what can be done with WebGL, so that you understand what WebGL as an API enables. Then I'm going to be introducing the QiCanvas 3D, which is basically implementation of WebGL inside Qt Quick environment. I'm then going to be showing a bit how you can use QiCanvas 3D as raw API on the kind of like WebGL level. Then I'm going to be really briefly talk about QiCanvas 3D and Three.JS, which is a higher level abstraction library that is built on top of WebGL. And then I'm going to be talking a bit about the future development that we are doing in around QiCanvas 3D. And then it's time for question and answers. So let's first talk about WebGL. What is the history and capabilities? So the WebGL is rather new because it was stable. The stable release was in 2013, but the initial release of the standard was done in 2011 by Khronos Group. Basically, Khronos Group is the non-profit technology consortium, and it manages various graphics-related APIs like OpenGL, OpenGL ES, OpenVG, and also WebGL. WebGL itself is a low-level state-based 3D vector graphics rendering API that allows you to call OpenGL ES label API calls from the make those calls from the HTML JavaScript side. And it is also often described as OpenGL ES2 for the web. Now, as a bit of history, when the standardization was being done, there was a lot of back and forth between should there be this low-level API or should there be a higher-level SceneGraph-based API. And there was proponents for each side. And basically, the consortium decided to go with the low-level API because it was seen as the key enabler for innovation. Usually higher-level APIs, they lock you into some set of features, some set of materials, some set of shaders that you can use. Of course, it would have been probably easier to port those over between different platforms, but it would lock you in, and there would be less innovation room to really invent new things to run in the environment. And I think this bet of choosing this low-level API, it has paid off really well. So if you look at, for example, where WebGL is available, it's basically everywhere. It's in every browser. All the big desktop browsers support it. Google Chrome, Mozilla, Safari, Opera, and even Internet Explorer nowadays. And it's also on the mobile side. With iOS 8, it's now in Safari. In the Android browser, it is available. It's also now available in the Windows Phone 8.1 and all the major competitors of these three leading platforms. So basically, you can say that WebGL is available everywhere on the web. Now, this has led to fantastic amount of innovation happening around WebGL. So if you look at, for example, scene graphs. So scene graphs are a way to do 3D on a higher level. So rather than just talk about, well, I want to draw a triangle. So first set this shader active in the GPU, set this texture active in the GPU. Now let's draw a few triangles, and then let's change the texture, let's change the shader, let's now draw a few more triangles, which is really, really tedious, and it's really highly specialized work. Not many people can do that. So scene graphs allow you to move to a next level where you say, well, let's create a camera. Let's place it here in the 3D scape. Let's load this object from the file. Let's put that in the 3D scape, and let's put the light in somewhere else in the 3D landscape, and then let's render the view through the camera. And that makes the whole 3D much more approachable. And as you can see, there are many different. If you go and look in the web, there are actually even more scene graph-based APIs available on top of WebGL. But I think these ones are the leading ones. Three.js is showing a lot of. I think there is a really active development going on there. Also in SceneJS, and O3D is a bit newer entrant, but it's backed by Google, so I think that it might carry some weight in the future. If you want to look, you can see there are a couple of links, basically the Khronos is listing all the different libraries and resources that are available that run on top of WebGL. And there is a really, really long list of all sorts of libraries that have been built on top of WebGL. Also, if you want to, you can go and look at, for example, Mozilla's website. It has a really great tutorial for WebGL, like getting started from drawing your first triangle to drawing your cube and then texturing it and lighting it and all that. If you are interested in that, that's a really good resource. Now, there are also some big projects that have been done with WebGL. I'm going to be showing you a couple of these. There is the Google Maps, for example. Many of you use Google Maps, and the enabling technology behind the whole 3D landscape of cities, that's WebGL based. Even AutoCAD has now offered their AutoCAD tool called AutoCAD 360 as an online tool, and it's also based on WebGL. And also, if you go to Chrome experiments, they have a separate section for WebGL experiments, and there is really beautiful things that have been done on top of WebGL API. Now, let's switch over to my browser, and I'll just briefly show you what are the capabilities of WebGL. So this is a view of the Manhattan in New York. I don't know how this translates through the video connection. But if you scroll through this, you can see that these buildings are actual 3D models. If we move a bit farther away, and you can see that this is to a normal user, I would say that this looks pretty photorealistic rendering even. But if we move on, there is another example of more like a, oops, seems I need to reload this, just a second. So this is a pretty famous website. I think that people who have been looking at WebGL probably have run across this. It's done by a company called +360°, and it's won quite a few awards. What they have here is basically a car visualizer where you can set the color of the car, and you can select the rims color, and you can select what car you are actually looking at. And it has pretty nice looking effects going on here. And this is actually one of the examples that has been built on top of Three.JS. And I'm going to be showing this running in our environment on top of QiCanvas 3D later on. Here is a application that has been done with a tool called Blend for Web, which basically allows you to implement a scene in the Blender using the Blender's game engine, and then export that as a WebGL application to be run on the browser. As you can see, there's quite a lot of going on. There are animated animals. The grass is swinging in the wind. You can walk around here. You can look at the water effects and everything. This is pretty impressive, considering that it's all JavaScript-based engine that is running here inside the browser.
And Pasi, just so you know, and so that everybody else knows, the performance might not look good on your computer, as this webcasting tool doesn't really provide us with a great way of we can't send 50, 60 frames per second. So animations that are smooth on the native application, even in a web service, aren't smooth over this webcast, unfortunately.
Yeah, thanks, Niels. That's a really good point. But as you can see here on the upper right corner, there's the frame counter, which is reading at the moment around 30 frames per second. And my machine, it's not the newest MacBook Pro. It's a couple of years old model, so it's not the latest and greatest, and it's still capable of running this at really nice interactive frame rates. Now, moving on. So let's move to the main topic, which is the QiCanvas 3D. And I'm going to describe what it is, why I implemented it, and how you can get it. So basically, QiCanvas 3D is a Qt module that you can, at the moment, it's provided as source code only. Later on in the final version, of course, we are going to be providing you with binary versions. But at the moment, it's a source code only component that you download, you compile it, and you do the make install step. And you have access to a 3D canvas from your Qt Quick scene that you can then add there. And then that allows you to do WebGL rendering by getting a WebGL-like context from the canvas component. Now, I'm stressing the word like because we are, at the moment, we implement all the functions from WebGL 1.0.2 API spec, but we have not been able to test for WebGL conformance, because the WebGL conformance tests, they are basically a bunch of HTML pages, and you really can't run HTML pages inside Qt Quick as natively. So we can't run those at the moment. This is one point where we are going to be looking at the customer input, whether the conformance is seen as something that our customers would like us to really reach for. And if that's the case, then we probably will have to look at how we could port over the tests. Traditionally, Khronos has been really open in the sense that they have allowed people to port conformance tests to different environments and then contribute those tests back and run and accepted the results of the conformance test after they have reviewed code. But this is not something we are at the moment looking. We are happy that we have the API implemented and it runs, at least at the moment, we have been able to run all the content that we have thrown at it. So why? People have been asking me, especially in the beginning, people asked me like, why? What's the point? I mean, we have WebGL inside our WebView, and you can add WebView into Qt Quick, and through that you could run WebGL. Well, my main point here was that, well, I've been doing quite a lot of stuff, especially before I joined DGI. I had my own company. I did quite a lot of private consulting, and I did quite a lot of work with WebGL. And I think that it is a really nice and productive environment for implementing 3D content, especially if you use a scene graph API like SceneJS or Threejs. Also, I think that Qt Quick is a really nice productive environment for doing 2.5D UIs. So in my mind, combining these two would make a really nice productive environment for making 3D content and combining that together with 2D UIs. Also, there is a lot of innovation going on around WebGL, so allowing porting of that content into Qt Quick and run it on top of QiCanvas 3D, I think that makes a lot of sense. QiCanvas 3D also, I mean, it allows you to reuse any existing 3D assets that you might have or you might get access to, or maybe you have a subcontractor that knows how to do WebGL but doesn't really know much about Qt Quick, and they can do 3D. Maybe you could, this would be a way to enable you to use their capabilities. Also, as I said, there's a lot of resources on the web on getting started with WebGL and more advanced tutorials with WebGL, and these all translate to QiCanvas 3D as well. So it provides a kind of a nice launch pad for getting into how to do stuff with QiCanvas 3D as well. And the whole point is that with this, you don't now have to add the whole WebEngine or WebView into your QML scene. You just to get WebGL-based content running. You can now do it natively inside Qt Quick without any HTML components in there. Now, also people have been asking me, well, what's the relationship between Qt 3D 2.0 that is now in the dev branch of Qt and its upcoming scene graph-based, native code-based implementation of a scene graph? And I've been saying that, well, I've been in constant communication with the KDAP people that are implementing Qt 3D, and we all see it as these two as complementary options. I mean, if you have something that is on top of WebGL, then QiCanvas 3D makes a lot of sense for you. On the other hand, if you have really heavy processing requirements, you want to be throwing around millions of polygons, or you want to do really complex lighting effects, or run really high complexity shader scenarios, then Qt 3D might be the best option for you. So it's they are all a bit different in how we approach. So if you later on, if you need to use 3D inside Qt, I would say please look at both. It depends really on what you're trying to do. For most use cases that we have seen, I would say that QiCanvas 3D is just fine, but we have also seen use cases where we are recommending people to use Qt 3D 2.0 instead. So QiCanvas 3D, so if you want to try it out, what are the requirements? So at the moment, QiCanvas 3D Preview, it compiles and runs on Qt 5.3 or later, and you need to have OpenGL ES2 or OpenGL ES2 capable GPU. And where you can get it, the easiest place to get it is to download the Qt 5.4 release candidate that we have out, because it's now included in that as source code only formats. Or if you want to really be on the bleeding edge, you can go and get the latest version from the URL there from code review and compile that. We are keeping it always compiling. It is part of the continuous integration machinery, so no commit goes through if it breaks compilation, so should be guaranteed to compile. And as I said before, when you build it, remember to add the make install step so that it really installs the component for you. And then open an example, build that, run, and then start looking at the code and start hacking. It should be really that simple. That's what we've been aiming at. So what are the differences between QiCanvas 3D and WebGL? Well, a lot of it is around naming and semantics. So WebGL, the specification, it talks about using HTML image element or HTML canvas element. whereas in QtCanvas 3D, we use custom textured 3D element. We have custom Canvas 3D element that you put into your QML scene. You can most of the time you can just think of it as different names with same semantics. Also, WebGL names objects with WebGL render buffer, WebGL program, whereas we name our objects as render buffer 3D, program 3D. This is just because we are not conformant and we don't feel comfortable using a Khronos branded name like WebGL. And luckily, none of the third-party libraries we have tried have any problem due to this. So none of the code that we have seen out there actually tries to look at the names of the objects returned from the API. So that should not cause you any problems. Also, WebGL depends on Java runtime environments, type arrays being there. The preview that is now out there with the 5.4 release candidate, it has a custom type array implementation. This was just a bit of unfortunate timing. We couldn't get the type array implementation into the Qt Quick Java runtime in time. So this is a workaround that we can use to work around with the issue that we need to still have an rather efficient way of passing big amounts of data from the native from the JavaScript into the native code. There is a slight difference in the API, but this is now issued with the preview, and it will be fixed by 5.5 because in 5.5 the Java runtime environment will have in Qt Quick also support for typed arrays natively. Now, how does this look from your point of view? Well, there's a lot of complexity under the hood. This is not something probably that you need to pay attention to. There's the two things that you need to pay attention to when you are using QtCanvas 3D. So you have the canvas element in your QML scene. It will receive two types of signals. One signal is the init.tl signal, and this is emitted if no context exists. So this is emitted once, and we are expecting you to do your initialization in JavaScript at this stage. So what you usually do is you get your GL context from the canvas element, you set up your GL state, you start any textures that you need loading up, or any modules that you are loading, you start loading those. And then after that, what you get is each time the canvas elements needs to be repainted, you get a render GL signal, and this is where you put all your rendering code. And this is emitted once for each frame to be rendered, and that's it. Those two things are the only things that you need to worry about really when you are using Canvas 3D. There is one catch in the scenario, and that is that if you don't call the Canvas get context API call in your init.gl, then you must at some point signal need render into canvas element to get the rendering loop going. This is just because we are expecting this to happen because the implementation is based on the behavior of typical WebGL apps. So typically WebGL apps, what they do, they have an initialization code somewhere in the HTML page that does exactly this. They get the context, they start loading textures and all that, and then they have a way of doing rendering at a certain rate. So we have been just making this a bit more simpler by offering these two handles, or sorry, two signals for you that you can hook to. Now, about using Canvas 3D. So the first thing you need to do in your QML code is you need to import it. So once you have compiled the source code, installed it, you do import Qt Canvas 3 1.0. Usually, we advise you to have your GL rendering code in the separate JavaScript file. We do this in all of our examples just because it keeps things clean. Usually, GL calls get, let's say, long. I mean, doing even a simple cube spinning on the screen takes really, really many OpenGL calls, and if you inline it in your QML, it can get really messy really fast. So this is why we usually do it like this. We set up a different JavaScript file and put everything in there. And usually we then just hook up the on init.gl call into an init.gl call in there, pass in the Canvas 3D, because usually you want to call the get context, for example, from Canvas 3D. and you want to query what is the size of the canvas 3D element, and even the pixel ratio, which is basically our way of supporting high definition displays. And you hook up your own render.gl call signal into rendering function of your JavaScript code, and that gets you going. There are a couple of logging flags that when you set these in the canvas 3D element, they are also set into the context that you get from the canvas element. Log all calls does what it says on the tin. It defaults to false, but basically if you enable that, you will get pretty extensive dump of all the calls that are being made into the canvas element. This is really useful because many times, because OpenGL is a state-based API, sometimes it is really difficult to figure out what happened in what order and what caused the problem that you are seeing a black screen instead of your spinning cube. So this has been really helpful. Also in OpenGL, usually the only way to get errors visible is to call gl.getErrors. Unfortunately, that is a pretty expensive call to make because it forces the pipeline, GPU pipeline, to be flushed and execute all the commands up to that point so that they really know whether there is an error happened, if an error has really happened at that point. So usually you want to avoid that. So that's why we have a way of recognizing most of the errors, maybe not all of the errors, but most of the errors we can recognize in our implementation, and we can then log them with really not that much of a cost because we are not stalling the GPU. So that's really useful flag, and it defaults to true. You might want to set it to false when you ship your code to your client, so just be aware of that. So in your JavaScript code then, during the initialization, as I said, usually you call the get context. The syntax is really exactly the same as it is in WebGL. You give a name. At the moment, this name is ignored. It can be WebGL, it can be Canvas 3D, whatever. But it is there just to be really API compliant with the WebGL. Then you can give attributes, like you can say, well, I want to have a div attachment in my rendering target, and I want to have anti-aliasing buffer also in my rendering target, and that's it. That sets it up. Texture loading is done. Now, if some of you saw my earlier presentation from the dev days, this was a bit different. I have changed this because I wanted to really model the texture loading closer to how it works with HTML, because this makes it easier to port over content from HTML into this world. So how it's done now is that you need to create a texture image factory like this. With that, so you create a new texture image with the texture image factory. With the texture image, usually you first set up your image loaded signal handler, which is done like this. And usually when the image is loaded, you usually want to get the cube texture, for example, create a texture. You want to then upload the texture into the actual GL texture that you have created and do all the initialization stuff. Usually you also want to detect whether the image loading has failed, so we have a signal for that, so you can connect to that and do whatever logging or whatever you want to do there. And then the image loading is started simply by saying text image source equals something. Usually you want to use resource files or even native files, but this is really really close to how HTML images are handling this, so should make life easier for you when you are porting content from the web. So in the actual rendering code, in our examples, you can see that what we are doing is we are handling the resizing of the canvas, because that can happen because QML layout can change if your user changes the size of your window, then the QML layout will change the size of your canvas element, and you of course need to react to that. And also we are reacting here to the possible change in the device pixel ratio, which is basically if you, for example, move a window on your Mac from a non-Retina display onto a Retina display, this will change usually from 1.0 to 2.0. And you need to detect that and handle it explicitly. And this is again to preserve compatibility with and be aligned with the actual WebGL specification, because WebGL specification tells us that we can't handle high definition displays automatically. It has to be done explicitly by the user of the API. But the rest of these, the calls then after this point, this is pretty, if you know your OpenGL, this should look pretty familiar, and then you clear your screen, and then you start doing your drawing after that. So let's look at the really simple code example. This is a textured cube. It's one of the examples in the QiCanvas 3D examples folder. So first of all, I would like to show you, if you have the 5.4 release candidate, this is where you can find QiCanvas 3D. So it's in the extras folder. It's in the top level, extras, QiCanvas 3D 1.0, source code. Just open this project file. I have it already open here. Remember to go to projects, add build step, make, install, and then build, and you're done. Then you can just go into one of the examples. So if you look at here, what I have open is the texture and light example. So let's build it. Let's run it. Again, on my screen, this is running perfectly smoothly at 60 frames per second. Probably over the video connection, it is not that smooth for you. Just have to take my word for it, or maybe download it and try it out yourself.
Yeah, it's true. On my screen, unfortunately, seeing it over the WebEx system, it's nothing near 60 frames per second. So that's a little bit of a shame, but that's the way the world works.
Right. So if we really briefly look at the QML file, you can see that what we have here. Sorry, I need to scroll here a bit. Let's get this a bit out of the way. So hopefully this is visible now, the code, and readable for you all. Nils, is that looking okay? Should I make it larger, smaller?
Sorry, I was muted there for a moment. It is a little bit small, so if you can make it a little bit larger, that would, there we go, this looks good, thank you.
Okay, thanks. So, as you can see, what we have here is the Canvas 3D element. It looks exactly like any other QML element. You anchor it to your parent, you do your stuff here. Here you see one of the tricks that we have done so that we can actually use Qt Quick animations to drive the 3D animation. So in here you can see that we have defined the animation rotation properties into the canvas element, which we are passing into the render.gl call. And here below you can see that we have a couple of sequential animations that animate the X and Y and Z orientations with some number animations, with easing and all this stuff, which is really nice because usually when you look at WebGL code that runs on the HTML, you have to implement all of this manually. You have to start implementing your own like sign-based easing as a JavaScript code, and it's really annoying. And this is really nice addition that you get when you port content from web into our environment, that you can now use all the nice animation enablers that we have in place. And as you can see, this looks exactly like in the PowerPoint code that I showed. Now, if we go into the texture light JavaScript file, scroll a bit here. So initialization, as I said, you get your context, you set up your OpenGL state. I'm not going to be going into detail into what these calls call. I would hope that you have some knowledge of OpenGL. If you don't have, don't worry, I'm going to be showing a bit easier way of doing 3D with QiCanvas 3D. But basically, if you know your OpenGL, this should look really familiar. You set up your viewport, which defines where the rendering goes. You initialize shaders, you initialize buffers. We create a text image. We set the handler for when it's loaded. What we do is when it's loaded, we create a texture, we bind the texture, we upload the data into that texture, and then we set some parameters like how the filtering works, and you could also set like wrapping, so does it tile over all the surfaces or not. And we have simple image loading field handler that just prints out, well, we do succeed from loading this picture, and then we set the source of that image, and that starts it loading. Now in our render.gl, again, should look familiar to you when you from the PowerPoint. We check the resizing of the screen or changing of the device pixel ratio. We go ahead and we clear our screen. Then we are using a third-party library called GL Matrix. You can choose whatever you like, but this is just something that happened to be available and seemed to be working really nicely. So I'm using that. So we are doing quite a lot of 3D matrix math here to translate and rotate the cube around the screen. And then we set these as an inputs to the shader code. And we also set the normal matrix into the shader code. And then we say GL draw elements and all the what the cube gets drawn with this call. So as you can see, just getting that cube running, it is a really lot of code. I mean, and I've even hidden quite a lot of the code that is still in here hidden. So it is a pretty involved task. And that's why I know that this might be an issue for many people, and I myself, usually when I want to like prototype something really quickly, I don't really want to be working in this level. So that's why I ported also the Three.JS library on top of QiCanvas 3D. So let me first describe what Three.JS is, how you can get this port, and I'm also going to be sharing some porting tips for you if you want to get some other 3D libraries or some other 3D content off the web and make it run inside Qt Quick. So Threejs it's basically one of the most active WebGL-based scene graph libraries out there. I think that they are averaging around 20 or 30 commits per day in development. It is really, really hectic development. And what I've done is just basically taken a snapshot from the 67 dev version, and there is the latest version is I think it's like 69 dev, and it has a lot of new API, a lot of new enablers. I haven't been able to get to work that to get box porting that, but it's the goal of getting that done also. So get the latest Three.js version in and working before we release the QiCanvas 3D along with Qt 5.5. And basically, Three.js it's implemented 100% with JavaScript, and it is really efficient. I've been debugging it quite a lot, and you can see that it is really efficient in how it calls WebGL. So it caches a lot of the state inside the JavaScript, so that it avoids making expensive calls through the into the native side unnecessarily. It caches the GL state so that it knows when it needs to enable or disable something, because usually state changes are really expensive in the OpenGL, because the driver then has to do quite a lot of validation and revalidation, and that costs performance, causes a performance hit. And also a lot of the WebGL content out there actually uses Three.js under the hood. So for example, the car visualizer that I showed that is using Three.js beneath the surface, so to speak. Now, how to get this? Here is the URL where you can get it at the moment. As you can see, this is a bit weird because this is my own GitHub page that I've loaned for this. We are actually at the moment thinking about bundling Three.js together with QiCanvas 3D. Probably in the first phase, we are going to be just including a working version of Three.js with the examples. And then later on, we are considering whether we should be bundling Three.js more like into the package itself. But at the moment, you can get it from here. Remember to get the stable version if you really want to recompile it yourself, because the experimental version, as I said, it's a working process of getting the 69 dev version working, so that's not at the moment working perfectly. So a couple of tips that I learned while I was doing this porting is that, first of all, with all these open source projects, this is a general rule, try to keep your delta small, because the libraries, they evolve really rapidly. So you probably want to implement like wrappers for HTML stuff like image elements. If you want to go and look at how I've done this with the Three.js, there are some examples how I did it there, and you feel free to. I mean, it's available under MIT license, just like Three.js. So feel free to go there and look how you could loan some of those components if you want to. Also, all the QtCanvas 3D objects are Q objects that I have exposed to Qt Quick. And this causes one problem, that you can't dynamically add attributes to these classes, these objects. So you can add things with array access methods. So for example, in Three.JS, what I have to do in some of the places is, for example, do this kind of a workaround where they are trying to add a belongs to attribute to the buffer object. So I just do it with this notation and define some value like 0 or 1 to the buffer belongs to attribute. It's a bit of a bore, but it works, and useful trick to get around this limitation. Also, you need to take into account that Qt imports all declared functions from the URL you give it. So be aware, the first line here, that is a declaration, function declaration. Below line, that is not a function declaration. And unfortunately, some of the libraries out there, they are using this notation as well to declare, for example, classes that they then use. So just to be aware, you might have to do some. This is actually really easy to do with a search and replace magic, but it is something that you need to take care of if you want to port that library over. And also, one of the things is that if you are running on mobile embedded devices, please take care of the memory usage. We ran into this when we were porting the car visualizer demo, and it basically loaded all the models in the beginning, and we had to change it so that actually dynamically loads only the model that is visible on the screen. So let's look at the car visualizer. I'm not going to be going into that code heavily because it is really involved. I just want to show it running, maybe show a little bit of the way how we have done it, and some of the differences, how it behaves a bit differently here in this environment. So as you can see, here is the exact same Ferrari California model. But what we have added wrong with the QML animations is, for example, again, apologies, this is running perfectly smoothly on my screen. Probably on your screen it is jerky, but that's just how this video casting works. But basically what we have done is all these are states in the QML side, and when we are switching the state from, for example, from interior camera to the side camera, we have animations going on, and those animations now control the 3D camera in the scene. But you can still grab the camera and you can zoom around in the scene. You can change the car. Oops, sorry. Okay, this is a bit weird. Sorry about this. This is a demo effect in effect. For some reason, the menus are appearing here. But
this is the way it always works when you are doing something live.
Exactly. So what we have done here is that, for example, when we change the color of the rims, we actually now change the camera view to show the rims, because that usually is more useful. And when you change the paint of the car, oops, sorry. This is now getting out of hand because getting the handle of that control there is a bit tricky. Got it? So now we change the camera view to show the actual paint of the car. And if we change the car model, you can see that we are doing it dynamically. So we unload the previous model and we load the new model, and we put this just this cover screen to hide the fact that we are doing that behind the scenes. Okay.
If I can just stop you for a brief moment, maybe showing that car model is actually a nice example of a question that we've got, and it seems some people are a little bit confused as to what the content here is, if it's only WebGL or if that is actually mixed then with standard Qt Quick and QML controls.
Yes.
So that you can interact with, for instance, the mouse, such as you were doing here in this example.
Okay, so let's take a really quick peek into the QML file. So it is a combination of 2D UI. All the buttons and controls you were seeing there, they were done with QML. So those are 2D controls in QML. The interaction with the 3D model that you were seeing spinning around, that is the car and the garage and all the lighting effects, that's done with WebGL. And a bit more specifically, it's done with Three.JS that runs on top of WebGL. So for example, if we look at the things here, so for example, all the color changes are animated. So we have animations for changing the color of the rims or the color of the car. We even modify the reflectivity of the car, so we can have a matte black or really shiny black color, for example. If you look at the, here is, for example, the state machine that handles all these different views. So, for example, we have the manual control state, which is where you are just spinning the car around with your mouse. Here's the interview, side view, front view, and all of these have property changes associated with it. And for each car, we have slightly different front views and rear views because the car models, they are different sized, so you can't use the same coordinates for all of these. Just adds a bit more to the complexity. But still, this is a lot more easier than trying to code your own animations in there. The actual interaction, originally we used exactly the same code from the JavaScript that the web page uses. And we were just passing the mouse X and Y coordinates into that code from here. Unfortunately, we ran into an issue that it didn't really support touch devices. So we ended up rolling our own mouse area-based control system. It behaves a lot like the one that is on the web page, but it is implemented with our own code. And here you can see what we are doing. We are just getting the X and Y coordinates. We are modifying the camera control pitch rotation, or the Z lookat position, and all these. It is a bit involved, but let's look at, for example, the here is the UI that you are seeing, the 2D UI. So we have a grid layout. We have the labels with just standard QML elements. We have the combo boxes that allow you to select the different car models. Some parameters for the car models are hidden in there. So basically, all of these are, the 2D UI is Qt Quick. The 3D stuff, that's done with Three.JS. Hopefully that clarifies this a bit.
Oh yeah, I think that's a very very good answer. There was also another question to the same area, if it's possible to use a QML object as a texture in the WebGL scene.
That is a nice segue into the next part and last part of my presentation, which is called Future of QiCanvas.
Brilliant.
So the current plans and feature requests that we had, so what are those? So future plans, things we are aiming at the moment, so we are currently working on top of 5.3 and 5.4, mostly on 5.4 now because it is really close to getting out there and the release candidate is pretty stable, so we are using that. As I said, the technology preview of QiCanvas 3D, it is now coming along with Qt 5.4. So as I showed you, go to the extras folder and you find it there. What we need to do more is even more content, have more content running on top and do more testing. We have squashed most of the major bugs that we had before the Berlin Dev Days time schedule. Then we had some crashing bugs on the Mac and some problems on Linux. We have fixed those. So it should be relatively stable, relatively ready to go. But still, QiCanvas 1.0 will be part of Qt 5.5. So that's when you get the final productized release, and it will compile and run only on Qt 5.5. And as I said earlier, the reason for that is that Qt 5.5 introduces the typed arrays into the Qt Quick JavaScript engine, and then we are going to be removing the QObject-based kind of a hackish approach that we have done so far with the technology preview. And we are going to be using the native typed arrays, which actually should offer even better performance, and mostly they are going to be it's going to offer us to reduction in the memory usage, because at the moment how we have implemented that causes us to have multiple copies of the data in the memory, and that is really wasteful. And so once we get to using typed arrays from the JavaScript engine, that all goes away and we get better performance as well. Now, as to getting rendering stuff from QML into the texture, Unfortunately, this is still in the not committed area. We have gotten this proposal and as an idea from Gunnar Sletta some time ago. But what this would mean would be that we would need to move all the OpenGL calls into the render thread. So what we are doing at the moment, we are actually rendering in the main thread and just rendering into an off-screen buffer, and then handing that over, that buffer handle over to the render thread, and then bleeding that to the screen. And this is just really a lot more convenient way of achieving this, because we need to be able to render from the main thread, call all these API calls from the main thread, because the main thread is the one that is running the JavaScript engine. So to get the calls moved to render thread, we would need to implement comment queuing, and this is actually not trivial, because we would need to implement syncing and stalling if any call requires it. For example, GL read pixels or GL get error. Both are examples of calls that if the user calls those, then you would need to handle that explicitly in our queuing implementation. But the benefit, if we do this, is that then we would be able to have any Qt Quick content running on the face of a queue. So basically, we could use any QSG texture provider as the texture source. So it could be an image, it could even be a shader effect source. So this is really something where we are listening to you. If you have the need, if you have the use cases, then I guess we just need to step up the game and start looking at this. But this is not going to be coming to 5.5, definitely not. But it could come in a future version if there's a lot of interest to this. Also, one of the benefits of doing this, if we decide to do it, is that we would no longer have to render through the FBO or off-screen surface. So that would mean better performance, of course. And also, it would mean that you could have anti-aliasing on mobile devices that usually don't support anti-aliasing buffer attachments into FBOs. Some other things that we are at the moment thinking about is maybe having profiling tools. So we have the profiling tools for Qt Quick in the creator, so would maybe make sense to have something similar specifically for QiCanvas 3D, maybe. We are looking at implementing extensions. There is a big registry for different extensions for WebGL, so we are looking at those, which ones might be the more critical ones that we would need to have. And also, one of the things that I mentioned before was that we are looking at maybe making Threejs part of Qt or QiCanvas 3D package, and maybe doing some sort of tooling there just to help you like import modules and then export those as JavaScript files that you can directly load into your QML scene. But these are all ideas, proposed things. And as I said, we are really looking for input on which ones you see as important ones.
I've gotten some questions as well on the nice car visualization example that you showed. Is there any way of downloading that Qt code and checking out what they can do there to start playing around with this type of API?
Unfortunately not. So the agreement that we have in place with the original creators of the content was that we are allowed to show the content running on our environment. We have all the copyrights in there, as you can see, and all that, but we agreed not to share the actual implementation. And if you go to their website and you download it, you actually see that their implementation is, I wouldn't call it encrypted, but it's just been made really hard to reverse engineer.
Obfuscated.
Sorry?
Obfuscated. Yeah, no, that's the way it is.
Right word. That was the word I was looking for, yes. So, unfortunately, no. But one of the things that we are going to be doing for 5.5 is, for the final release, is that we have now decided that we are going to be adding examples that use Three.JS as a library. So you are going to be getting examples showing you how to use Three.JS together with Qt, with the QiCanvas 3D. Okay, and that's all. So recap, I talked about what is WebGL, showed you a bit like what can be done with it. I introduced the QiCanvas 3D, showed you a bit how to use that, showed the code example. talked about the Three.JS pod that is available on top of QiCanvas 3D, showed that nice car example as one example that can be implemented also on top of Three.JS, and talked about the future. And any more questions?
Let me unmute, and then, yeah, there are a couple of questions here that might be interesting. I think you've actually answered several of them throughout the session. A lot of people were interested if you could implement, for instance, QML content on the side of the cube that you were spinning around in the end, and I think you quite expressly explained that now in the end. Also, there were some questions regarding, for instance, Open Inventor, Coin3D, and other similar libraries, and how QtCanvas 3D compares to some of those, if you have some insight or information to share regarding that. I don't know how.
Yeah, so my understanding, Open Inventor and those are basically higher level libraries than QtCanvas 3D. So QtCanvas 3D, you can think of it as WebGL for QML. Nothing else, nothing more. That's it.
Okay. And that brings us to the next question, which is more going on to the API level of WebGL, but someone wondering, isn't it a bit weird to implement an API like WebGL on top of the scene graph like Qt Quick? It wouldn't be better to stick with the declarative way of doing things to begin with, rather than calling GL from a JavaScript framework? So I don't know if you have any thoughts on that or good use cases where this.
Excellent question.
Yeah.
I was painfully aware of this clashing of paradigms when I implemented the first prototype of this, and that is really true. Usually, how people are taught or are thinking about Qt Quick is really that you set up the state and you let the scene graph engine run, and you don't do this sort of heavy rendering calls from the JavaScript itself. But it turned out that actually, well, what I did first was I implemented really a simple version of the API, started to get the cube running, and I was really skeptical myself about this approach. Like, well, will it make any sense? Will it perform? Will it basically offer anything useful? And I was really positively surprised how efficient the V4 VM that we have, the JavaScript engine that we have, is. So I was really surprised that, well, actually it goes against the paradigm, but it still allows you to do really nice looking stuff at high frame rates, even on mobile devices. So we have that car demo running on, for example, Nexus 5, runs really smoothly. We have it running on iPhone 5S, runs really smoothly. So I was surprised myself how well it works. So I just decided, well, it goes against the paradigm, but it works and it offers a really nice way of doing 3D, so let's go for it. And I haven't heard anybody inside the company, at least, saying anything against that.
No, definitely not. So thank you very much on that little bombshell, as they say in a famous TV show. Then I think we're drawing near the end of our time here. Thank you very much, Pasi, for sharing your thoughts and sharing your code and your ideas with us here today.
You are most welcome.
And yeah, with that, I'll think this part of the session can be counted as concluded.